me bang. And we pretty much amazing. Yeah. Mind your manners, you hear me? And all the people should be raising their glasses. Flow crazy, celebrating the madness. I never thought I would deliver no classics. Then I hooked up with them and they delivered more classics. I've been keeping it true. Hotel good, long as I can peep on the view. Like, damn, how high are we? You gotta gamble in this life, Charles Bar. I'm overprotected, do the dopest of methods. Now my vocal perfected, this is audio breakfast. Yes, so tell a hater here's a slammer. I know they hating on us, but mind your manners. Take a second look and you'll see. There is no one like me. There is no one like me. Like me. You better reconsider. You will never do better. There is no one like me. There's no one like me.
How's it going, Mr. Howard?
What's up, Howard?
I'm Physic, and
I'm Phil.
this is Phil, and this is here. All we're doing is just declaring the variables. So H1 is the height of the dropped roll, so the one that doesn't get unrolled. We had that at 7.8685 feet, and we'll get to that later. H2 is the height of the unrolled roll, so the one that we're going to roll to the ground. D is the inner diameter of the toilet paper, and big D is the outer diameter. Theta was equal to 0 in order to get sine of theta is 1, so we needed to just declare that. And the mass of both of the toilet paper rolls is 0.108 kilograms or 108 grams. All we're doing here is we're given this equation. We've been using it for quite a long time. Net torque is equal to force times radius times the sine of theta. We're just letting you know here that R is equal to big D. We use diameter by accident. We should have used radius first, but we ended up going through with it and it ended up working perfectly. So basically net torque is equal to force times outer diameter times the sine of theta. We already said theta is equal to 0, which means sine of theta is 1. And we also know that force is equal to mass times gravity, and mass times acceleration, in this case gravity. So from that we concluded that net torque is equal to mass times gravity times outer diameter. Right here, this equation is actually given to us on our green/white sheet. Delta x is equal to initial velocity times time plus the 1/2 acceleration times time squared. Now obviously our initial velocity is 0 because we're holding them, so we just got rid of that part. Delta x is the same thing as height, so height is equal to 1/2 AT squared. From that you can derive that t, time, is equal to the square root of 2h over a. So over here, the time of the dropped roll is the square root of 2h1, because we already established that, over g, and the time of the unrolled roll is the square root of 2h2 over a. The reason why it's over g and over a is this one's acceleration is gravity, but for the unrolled roll it's gravity and angular acceleration because it's being unrolled in the process. And from there we concluded that the ratio between heights is the same thing as the ratio between the two separate accelerations for each toilet paper roll.
Alright, so another equation that we learned during rotational kinematics is that the total or net torque is equal to the moment of inertia times angular acceleration, and you, luckily enough, gave us the moment of inertia of the unraveling roll, which is the only thing that has angular acceleration or torque. So we just changed this equation and we set it as angular acceleration is equal to net torque over moment of inertia. Now net torque we solve for over there with Sarthak is equal to mass times gravity times the outer diameter. And the moment of inertia is right here given. We plugged that in. So we took that and we plugged in the variables that we do know, most of the variables. We plugged in mass, which is 0.108 kilograms times gravity times a big D all over this, which is equal to 2g big D all over little d squared plus 3 big D squared. Now keep in mind that this is still equal to angular acceleration from the very beginning. We've just rewrote it. So we also know that translational acceleration is equal to angular acceleration times big D. So we plugged that in. We plugged in our angular acceleration here and times it by d. So we just get d squared. That's the only thing that changes. So the acceleration of the unraveling roll is 2 times gravity times the outer diameter squared all over inner diameter squared plus 3 times the outer diameter squared, right here.
We're rolling.
Oh, okay. So we took this equation up here, the ratio between the heights is equal to the ratio between the accelerations. This one is the acceleration is just gravity because of free fall, as shown up here, and this one we just put acceleration because it's the acceleration due to free fall or gravity just in free fall plus the angular acceleration that it has. So we solved for A previously. So all we did was plug in A here and then G up here. Now the two G's cancel as you figure that out, and you get inner diameter squared plus 3 times outer diameter squared all over 2 outer diameter squared. Now, we measured the toilet paper roll and got our inner and outer diameters, which we have here. We plugged it into this, we moved it over. Then if you solve for that, you get very small decimals. And if you divide those, you get 1.5737, which is the ratio between the heights due to the difference in acceleration. So we picked our baseline for the unraveling toilet paper to be at 5 feet. So we took 5 feet and multiplied it by our ratio, which is 1.5737, and we got 7.8625 feet. So we knew that 7.8625 feet is where the roll that is not unraveling will be dropped from, and then 5 feet is where the unraveling roll will be dropped from, and then they will land at the exact same time. Alright, Howard, this is our conclusion. So we got a ratio, as we explained it. The only problem that we may or may not have had with this experiment is that without even realizing it, we used diameter the entire time and didn't even think that we should have been using radius. Except, after everything was said and done, the toilet papers landed at the exact same time. I'm beginning to believe that if you use diameter on the whole problem, or radius on the whole problem, we get the same answer. So I don't think we have any problems. Yeah.
But in conclusion, this ratio can be used at any height using any units, centimeters, yards, kilometers, to determine how high the drop roll should be and the unrolled, unraveling toilet paper roll should be, in order for them to land at the exact same time, regardless of the fact that if it's radius or diameter, as we've proven in this case.